Well, good afternoon, everyone. I'm Jason Gibson, CCO at IACMI. Innovation Insights is our monthly webinar series highlighting the people, ideas, and partnerships driving advances in composites and manufacturing across the U.S. As part of the Manufacturing USA Network, IACMI leads national efforts to scale new materials, develop sustainable processes, and strengthen U.S. manufacturing competitiveness. At IACMI, our mission is to convene, connect, and catalyze. We convene the composites community to share ideas and opportunities, connect industry, academia, and national labs, and catalyze real progress through collaboration and commercialization. Today's Innovation Insights reflects that mission, highlighting new ideas, technologies, and applications driving the future of composites. For those new to ACME, we accelerate composite innovation to strengthen U.S. manufacturing and workforce competitiveness through co-funded projects, access to world-class facilities, and a powerful national network. So if you're listening today and you're not currently an IACME member, we encourage you to consider the value of joining. When you become an IACME member, you gain more than an affiliation. You join a national network accelerating innovation in composites and advanced manufacturing. Our working groups connect leading companies, researchers, and government partners to share insights, identify opportunities, and shape technical priorities. Membership provides access to real-world expertise, project collaboration pathways, and visibility into funding and commercialization strategies. Whether you're developing new materials, scaling production, or entering emerging markets, IACME gives you a platform to engage, contribute, and make an impact. We'd be excited to welcome you into our community, so please visit our website and reach out to us by filling out the online form. Now, if this is your first time attending, we encourage you to explore past episodes that are available on our website. Since its launch, Innovation Insights has convened members and partners from across the composites ecosystem to share practical applications, emerging technologies, and lessons learned from active R&D and commercialization efforts. This series is designed to keep you current on industry trends while creating direct access to the people and ideas shaping the next generation of composite materials and manufacturing technologies. And today is a good example of that. So let me introduce our speakers for today. Today's Innovation Insights features three presenters pushing the boundaries of composite manufacturing, sustainability, and advanced materials. We'll look at new approaches to reusing large format additive tooling and examine two powerful emerging nanomaterials, aligned carbon nanotubes and boron nitride nanotubes, both creating exciting possibilities for improving composite performance. We'll begin with Carl Aune, Director of Business Development at Epic Advanced Materials. Carl will present boron nitride nanotubes and how they provide enhanced performance for advanced composite applications. He'll show how BNNTs deliver exceptional thermal stability, electrical insulation, reinforcement, and share examples of where these materials are being deployed to meet next-generation aerospace, electronics, and high-temperature challenges. Next, Dr. Kevin Retz, Business Manager for NAWAH, will cover architecture nanomaterials built from vertically aligned carbon nanotubes. He'll show how this organized nanotube structure dramatically boosts mechanical, thermal, and electrical properties in composites and highlight emerging applications in mobility, energy, aerospace, and other performance-driven sectors. And then we'll close out with Dr. Matt Corey, R&D staff at Oak Ridge National Laboratory and Assistant Professor at the University of Tennessee. Dr. Corey will discuss efforts to recycle and repurpose thermoplastic composite tooling produced through large format additive manufacturing. He'll share results from pilot and industrial demonstrations and the benefits of establishing circularity in composite production. So with that said, I'd like to go ahead and stop sharing and I'll turn it over to Carl Aune. Carl, go ahead and feel free to share your presentation.
All right. Is it coming up?
It looks good.
Excellent. Well, Jason, thank you for that introduction, and thank you for the opportunity to be here today to discuss boron nitride nanotubes. What is a boron nitride nanotube? They were based on the discovery and synthesis of carbon nanotubes in 1991, theoretically documented in 94, and first synthesized in 95 in a laboratory. Where are we today? We have 13 global companies in various stages of commercialization. And as Jason mentioned, I work for Epic Advanced Materials, which is one of those 13. The graph there kind of shows the amount of papers that have been written for academic purposes and application purposes since 1995. There's over 15,000 papers in academia. So a lot of information out there. So again, boron nitride nanotubes are analogous to carbon nanotubes. That's where they came from. Discovering that the CNTs came to the work on BNNTs. They overlap in this Venn diagram from high strength, high stiffness, high thermal conductivity, high aspect ratio, and low density. Where they differ is BNNTs have a little bit higher oxidation level at 900 C in air, no absorption in the visible spectrum. They're electrically insulative. They have high neutron absorption, so think of medical applications in space also. White in color and non-cytotoxic. Boron nitride nanotubes are an allotope of hexagonal boron nitride. By adding a lot of energy to that, you turn them into these crystalline tubular structures. We call them a super material at Epic because they're 10,000 times thinner than a human hair, 100 times stronger than steel, and 1/6 the weight of steel. Again, talking about carbon nanotubes versus boron nitride nanotubes, last year there was only 15 kilograms sold in the entire commercial global market. Compare that to the 4,000 metric tons of carbon nanotubes that were sold. BNNT properties, they're white. Again, crystalline concentric circles. They're somewhere in between 3 to 7 nanometers in diameter and about 10 microns long, 5 to 10 microns long. Their density is about 1.4 grams per cc. What separates them on the mechanical properties is the incredible Young's modulus strength and the tensile strength. And I'll talk a little bit more about the thermal conductivity. So EPIC stands for Enhanced Pressure Inductively Coupled Plasma. That is our reactor there in the picture. That is one of many ways to make a BNNT. There's also arc discharge, laser ablation, chemical vapor deposition, and ball mill annealing. The benefits of our system is it offers high production rates, no catalyst, no metal contaminants. We also use machine learning for optimization of production and quality control. So AI is taking over a little bit of that portion. Epic's BNNTs have a high aspect ratio. So again, that aspect ratio and purity is key to any kind of success in a resin system. The reason for that is that the higher the aspect ratio, the better the percolation of photons across the matrix, and also how it acts as a nanofiber to hold the matrix together. We do functionalization for specific applications, specific resin systems, and I'll get into that a little bit more when we talk about blending. We offer customized forms, so in powders, liquids, and solid dispersions, depending on what the customer is end use is. That is a picture of our nanotubes on the right-hand side. You can see the tiny little tubes across the matrix. That's what we're looking for, long aspect ratio. What are BNNTs? They are an additive. What differentiates them from regular fillers that help with thermal conductivity is that they provide great results at a very low loading. So instead of 20 to 70% of metal oxides or hexagonal boron nitride, the value proposition is a small amount goes a very long way. So what we found is the low-lying fruit in the marketplace is in electronics because of the thermal management properties that the BNNTs offer. So we are targeting potting compounds, encapsulants, thermal interface materials, gap filling compounds, and underfill resin systems in electronics. So that's our first go-to. Let's talk a little bit about thermal conductivity and how it works. So initially, you have your epoxy resin there on the left-hand side, and it's basically an insulator. Start adding BNNTs, and you start getting to a percolation threshold, which is where the BNNTs are touching each other, and then it creates a conductive zone. Uh, I, I want to point out the chart on the top right-hand side, which shows BNNTs at 1.5, 2, and 2.5%. Notice that as you start adding the BNNTs into the matrix material, you start getting higher and higher thermal conductivity. But there becomes a point of too much is not a good thing. So when you get to about 2.5% in this specific matrix, you start losing some of the thermal conductivity from the scattering of the heat through the matrix rather than the transferring of the heat through the matrix. So again, our value proposition initially is the percolation network provided by the BNNTs to take from the heat from a microprocessor across the resin system to whatever the heat sink material may be to keep that processor cool and running at max capacity. What other targets that BNNTs can fit in? What other markets? Coatings. So again, BNNTs could work as coatings in high temperature pipes and tanks. Corrosive chemicals for oil and gas, or any corrosive chemical for that matter. We're looking at adhesives and sealants for their high strength properties. Pre-preg resins, where they're coated on the outside of a fabric. They're not good for infusion resins because obviously it turns into almost a filtration system where your BNNTs clump up and clog one side of it and don't infuse properly. They're great in the battery and electric vehicles exactly for those insulation zones and heat management properties that the BNNTs offer. And then in composite radomes, we are looking at that also with a program that we're working on where BNNTs are radio frequency transparent, so they can improve the strength of a resin system on a radome, but not create any kind of blockage to the RF signals. So how are they incorporated into a polymer matrix? We functionalize the BNNTs using a plasma system. We add a chemistry that's dependent on the chemistry that it's going into, whatever that application may be. We then blend that together, mix it, catalyze, and you get your BNNT infused matrix that gives you those enhanced properties. As you can see in the image there, you get these bridging of the BNNTs through the matrix that improve strength, improve the thermal conductivity, and so forth. So in mechanical properties, I just want to show a couple examples. Here's a polystyrene and a PVA, where adding the BNNTs improves Young's modulus and tensile strength. Each resin system incorporates these BNNTs differently, and the results are different. Sometimes you require half a weight percent of material, sometimes all the way up to 5 weight percent of material, depending on the resin system and the results desired. Flame retardancy. I love this origami aircraft here, this little paper airplane. You can see the regular paper in 10 seconds just absolutely gets burnt. And then with carbon nanotubes, it lasts a little longer, about 60 seconds. With BNNT paper, with the torch on there, it lasted over 2 minutes. Also, a product called Celligard, which is used as a coating material for electronics. The bottom graph there, picture shows the Siligard coated on both sides with BNNTs and exposed to the same flame, and how it actually protects the Siligard from the heat source. Chemical resistance, here you have a 2.5 weight percent of BNNTs added into a waterborne polyurethane with a 30% nitric acid solution. The pictures tell you a clear story. After 5 hours, there's very little damage to the coating that's covering the electronics. We believe this to be based on the outer layer. Think of the outer skin layer of the polyurethane gets taken away by the nitric acid, exposing the BNNTs that then create a high contact angle over an incredible range of, or the entire range of pH. And this same property helps with hydrophobicity and oil phobicity. Um, so, key takeaways: improved thermal conductivity without electrical conductivity, increased mechanical strength and stiffness, improved heat resistance and flame retardancy, improved chemical resistance, hydrophobicity, oil phobicity. Keep in mind, every resin system requires testing. Every application requires testing. And there's always the question, well, how much does it cost? What's the money? Well, carbon nanotubes versus production rates. Historically, in 2000, they were $1,200 a gram, and now they're around $1 a gram. And BNNTs, we believe we are right around $300 to $1,800 a gram, depending on the level of purity. So it gives you an idea that of historically, we're about at 2005 with BNNTs, both in level of production for commercial applications and the cost of the materials currently. But we foresee that coming down with the use of with the higher production levels. And that's my presentation, folks. Thank you for sitting through there.
Well, thanks, Carl. That's really interesting information. So it appears, well, first off, I want to mention to the audience, if you have any questions, feel free to throw them into the chat and we'll ask them to the presenters as we get to them. But it appears you're starting off with the electronics area for the thermal conductivity reasons, but incredible opportunities with mechanical enhancement and then the fire retardancy. Where do you see the marketplace growing for you guys at Epic Advanced Materials in the near future?
The immediate future is going to be electronics, due to the fact that chipsets are becoming better and better, smaller and smaller, so their thermal footprint is larger as they get smaller. So to remove that heat from that chipset requires a higher level of conductivity, thermal conductivity. So also, BNNTs are inert and not electrically conductive, so they do not affect the actual chips themselves when added to the resin system, whether it's a silicone, a urethane, or epoxy that's used to coat that chipset. And as I mentioned in one of my slides, then I think the next easiest thing will be coatings for us to get involved with. And then from there, probably a little bit more of the traditional composites, which are resins with a fiber reinforced matrix. We haven't crossed that bridge yet, and there's a lot of science that needs to get behind that before we get in there.
Great. Next thing, as far as capacity, I know you're just starting up in essence, but can you give us a feel for what your capacity is and what you hope to expand to in the future?
Absolutely. So good question, because that's what everybody asks. Well, hey, we like your product. We want to buy a bunch of it. How much can you make? Well, you saw a picture of one of our reactors in the slideshow. We have two of those. One reactor at a single shift can make 10 kilograms a year. The yearly commercial demand is about 15 kilograms. So with both reactors, we can actually make 5 kilograms in excess of global usage. That's with a single shift. We can double shift, triple shift, and keep those machines running. So we're probably maxed out at about 30 to 40 kilograms a year before we have to CapEx into some more reactors.
Okay. And then you mentioned how you functionalize. is your functionalization pretty customized? In other words, can you work with any epoxy, or do you need to re-optimize your functionalization if somebody brings you a different epoxy than what you've worked with in the past?
That's a great question. Excellent question. So yes, functionalization is very much based on each chemistry. Um, Whether you're using a Novolac or you're using a Bizet or what you're using, or a silicone or a urethane, whatever that may be, that functionalization is very much customized to the customer's product. So we always say, hey, please send us in a 100-gram sample of your resin, and we'll start playing around with a functionalization portion to see what actually works before we send a test sample to the customer for them to put into whatever application they desire.
Great. Well, I appreciate
Jason,
you sharing all that info. For everyone listening, feel free to reach out to Carl if you'd like further information. But let's go ahead and turn it over to Dr. Kevin Retz next, and he's going to talk about the NAWAH aligned carbon nanotubes. So, Kevin, feel free to share your screen.
Okay, can you see my screen?
It's not in presentation mode, but we can see your PowerPoint.
You should be in presentation mode now.
Yeah. There we go. Looks good.
Okay, great. Good afternoon, and thank you for joining the IACMI meeting this afternoon. So I'm going to go over NAWAH and where we are today with developing vertically aligned carbon nanotubes and industrialization. The core product that NAWAH makes is vertically aligned carbon nanotubes. And we have the ability to keep that vertical alignment when we grow the carbon nanotubes and also when we transfer them into a product. And we've worked with CEA in France, MIT, UDRI to help develop the technology and then also the ability to scale up. Some of the background real quick. NAWAH technology started with as a spinoff from CEA. N12 was a spinoff from MIT. And those companies combined in 2020. And then in 2023, NAWAH was formalized to industrialize the product. So parent company is in France, Rosé, and I'm responsible for setting up US operations here in Dayton, Ohio. So where are we? Currently, we purchased a building in the end of May this year. We were moved into phase one of that building. It's roughly 23,000 square feet that we've moved into. And we are going from right now at UDRI, I have the ability to produce 10,000 square meters a year. With the equipment we're installing here at this facility at 35 Rock Ridge in Inglewood, which is out by the Dayton Airport, we'll be able to go to 400,000 square meters of material. To put that in perspective, that's 75 football fields of material. So picture of part of the furnace on top, and then just some of the other support equipment that we have going in. Again, we will be fully online the end of January. Right now, we're going through the initial trials with both the furnace and some of the support equipment currently now. So we grow the vertically aligned carbon nanotubes, so what? Why? The picture on the bottom shows it best. we have a carbon ply of carbon fiber coming out at you. And we have one carbon fiber going across the bottom of the pitcher. In between, you can see the vertically lined carbon nanotubes. We create that structural bridge from ply to ply, fiber to fiber. So we're creating that structural bridge. By creating that structural bridge, we're changing the dynamic of the failure modes in the composite. The photo on the left is a traditional semi-toughened system where the crack propagation unzips in between two plies. The same material system on the right, it can't unzip in between the two plies. You got to go through all those carbon nanotubes. So it looks for a path of least resistance, which turns to be intra-ply, looking for the resin in between the fibers. So we're changing the dynamics of the failure mode. What that does if it is a resin-dominated property, that's where the vertically lined carbon nanotubes work. If it is a fiber-dominated property, no. So we're not changing the dynamic of the fiber itself. We're changing the dynamic of the system, predominantly the resin area. So as you can see at the very bottom, short beam shear on a 0-degree panel, we're not getting a lot of improvement because there it's mostly fiber dominated. But you start getting into compression after impact, then you're getting into 12% or plus. Fatigue, we greatly increase. The top one worked with a customer that was 760 cycles where they were failing. We took it up to over 12,000. Impacts another area. So the chart on the right shows 10 impacts with a panel that had the carbon nanotubes added to it. That's equivalent to the very first impact. So things like barely visible impact damage for aircraft, which is a critical design feature, we help change that. Compression after impact, things like that. We've done testing all the way down to negative 320, and we've done elevated temperature testing. The presenter before showed oxidation. You got to keep that in mind. So there is limitations on the vertically aligned carbon nanotubes as there is with any material. But at negative 320 degrees, we showed that we greatly reduced the amount of microcracking and that the microcracks didn't link up, which helps with permeability. And they were 20% higher on the strain level before they even started. That then gives the design engineer an area where he can actually start to think about designing things like cryo tanks, high pressure tanks, where they're not getting the microcracking. With NAWAH stitch, where you can change where you put the material in a layup, because what we do is we transfer the carbon nanotubes into a pre-preg, a resin film, or a veil cloth, and then the customer can help apply it where he needs it. But what the carbon nanotubes do is that we increase the electrical and the thermal conductivity in both the X, Y, and the Z direction. So we're giving you thermal and electrical conductivity throughout the composite panel, giving you the ability to have a multifunctional structure. To emphasize this, the panel on the lower left, that was a fiberglass panel that we completely cured and under a vacuum bag by putting an electrical current into it. There you can think of things like tool faces, field repairs. The one on the right is a wing leading edge. We were able to, again, build the leading edge, put the carbon nanotubes in it, and put an electrical current in it to shed ice. We've done that with the propeller blade, and there the one test we had to pass was run it for 24 hours nonstop, draw less than 20 amps on power, and keep it at 125 degrees for an anti-icing mode. The other advantage this gives you, because the thermal conductivity is so uniform throughout the panel, you can use it for inspection. As it takes a damage, you change the resistance or you change the thermal profile that you see on the part. Therefore, you can help monitor the structure or check it for the damage that you're recording through resistance check. The operations that we're going to will be roll to roll. So we will be able to produce the carbon nanotubes on a roll, transfer them into a roll of prepreg, resin film that we're developing, or a veil cloth. The pictures on the lower side left, that shows the carbon nanotubes in a resin film. When we transfer that into a part, we keep that vertical alignment. And the picture on the right shows that even in more detail, where you can see the carbon nanotubes. They've kept their orientation. Therefore, you keep the properties. Here are some of the results for a veil cloth. This is very important for things like bonding, surface prep, also for resin infusion. We have the photo on the left. That's of the carbon nanotubes before being transferred. That's after being transferred into the veil in the middle. And the SEM showing that we keep that vertical alignment. And we keep the electrical and the thermal conductivity. Other areas that we're looking at, stay tuned. So we're looking at not only composites, but other potential areas and applications. Market areas that we are currently actively in discussions with customers. Everything from advanced air mobility, microelectronics, to sporting goods. We're talking across the board. The carbon nanotubes are extremely versatile, and they give you the thermoelectrical and the mechanical properties improvements. Again, we're in the area of scaling up. We're going from the 10,000 square meters up to 400,000 square meters a year here at the Dayton facility. The facility in France will go from the current rate of 10,000 to 400,000 by the middle of next year, the end of June, July of 2026. So I want to thank you for your time and open for discussions.
Thank you, Kevin. Few questions for you. So you've got incredible capabilities there with the enhancement it can do, and you've got a lot of different market segments that you've already started approaching. If you had to pick one that you feel like you had the best value proposition for because of those physical properties, and you wish that they'd be more aware of what you're able to do, what would that be? Kind of give me a feel for where you'd like to grow the most in.
Excellent question. There's reason we're talking across the board is because the material has wide applications. Our very first applications that will be coming up and announced will be in sporting goods. But we're also very active in the air mobility, automotive, and aerospace. But those market segments take time because of regulatory to get in there. We're working very early on several programs, and we're on the material qualification steps in several programs in all three of those areas. But that just takes time. And so that's why right now we're not focused in just aerospace or focused on air mobility. We're building that ground block with sporting goods and some of the others. But then we've also caught the attention of some microelectronics because of the thermal conductivity and the enhancements we can give to some of their base materials from a mechanical standpoint.
Okay.
So if you have a challenge, would love to talk to you. If you have a material challenge, be it mechanical with composite materials, thermal, electrical, would love to talk to you.
Okay. So let's take that question then, and let's say I'm a sports and rec manufacturer and I'm utilizing prepreg now. What's your preferred method of engagement? Do you want us to send you our prepreg and you incorporate it, or should we work from you to buy the prepreg directly from you, or how do you prefer to go to market for those customers?
Couple of things. First, I'd like to have the discussion with you. And if you're working with a prepreg now, we can transfer into your prepreg, send the prepreg to us. We'll transfer the carbon nanotubes into it. We can ship it back. We are also developing the resin film, and those are in field trials currently, and the veil cloth, depending on your manufacturing process. And that will be a product that is, both of those are shelf stable. And so they'll be able to stay on your shelf for 12 months or plus. And then you can interleaf it where you need it or transfer it into your prepreg and utilize it that way. So let's have the discussion and we can see how we can work with you now and what's best down the road. Okay. Also, you don't need to put the carbon nanotubes everywhere. We can tailor the response based on your needs, be it a fatigue issue, a damage issue, a cosmetic issue in certain places. So you can tailor your utilization to meet your requirements.
Great, great. Well, appreciate it. Thank you for the information. And we're going to go ahead and turn it over now